Hello everyone. Today we're going to talk about the second test flight of my rocket Shock. This rocket uses aft fin control to steer itself through the air and orient vertically. There were a couple of changes I made after the first test flight, including removal of the mid-body wings. These wings used to sit right here in the middle of the rocket, and they increased its lift coefficient, but they decreased its stability, so they were removed. I saved a little bit of weight doing that, but not too much. I replaced them with these little plastic plugs. They're just held in there by friction. I thought that might reduce the drag, but it probably didn't do a whole lot. I also replaced a lot of the load-bearing and critical 3D prints with a stronger and more rigid material. So everything from the fin and motor mount assembly to the actuated fins to the static waist fins, they were all printed out of PETG, which has a high enough melting temperature that the motor won't melt it, but it's pretty flimsy. I can just bend these with my hand. I don't know if that's very visible, but I wanted to replace these wings and the fins and the motor mount with something more rigid, and so I chose carbon fiber filled polycarbonate. This is from 3DX Tech. It is incredibly strong, incredibly rigid, and I can print it pretty easily. In the past, I've also made things out of carbon fiber nylon, including this motor retainer, but the nylon is significantly bendier, and it didn't have the rigidity that I needed for a lot of these structural components, but CFPC solved all those problems. So today we're going to talk about all of these additions in detail, and then we're going to look at some flight footage and then do some analysis, because this flight did not go perfectly, but that's okay. So for this flight, I wanted to reduce the mass of the vehicle and prepare to use some higher thrust motors in the future, motors with more thrust than the G33 and H42s that I've been flying on so far. So first things first, I printed the fin and motor mount assembly, which is the gray structure there, out of CFPC. This does a bunch of important jobs. First of all, it's the motor mount, so it needs to handle motor loads, and it does get very, very hot after the motor fires. It transfers those loads into the main body tube via the thrust ring at the bottom, and then it also holds the servo actuators for the fins, the fin linkage mechanism, and then the bearings on which the fin rotates. So I printed this. It turned out great on my Bambu Lab X1, and then I decided to try to print all of those very tiny linkage elements out of CFPC as well. Some of these turned out good, some of them didn't. But after that, I finally got to the actuated fins and the waist fins to round out the matte black look on the back of the vehicle. And then, the day before flight, I decided that it would be a really good idea to tear the vehicle apart and reassemble it with all of these new components, which took way longer than I expected, and there was a couple hiccups along the way. I also printed a new main battery mount that has a couple of mounting holes and a little mounting bracket, so that I can put a little GPS receiver board on it. And then on the top of the battery mount, there's a little spot for a GPS chip antenna. This is an ongoing project. I'd like to incorporate GPS updates into the vehicle. It does require me to align some reference frames, and unfortunately, I didn't get some of the math quite right in code for this flight. So the GPS does work, and it gave me terrible data, but that's okay. So I have been putting all of these little elements of the linkage mechanism and reinstalling the fins in this new motor mount, and made several discoveries, which I probably should have known beforehand, but that's okay. So this new material, carbon fiber polycarbonate, is more rigid and it is stronger than PETG, which is what the previous version right here was made out of. I like it to, I want it to be strong and rigid, and I like the strength and rigidity that the material has. But some downsides are that when I designed these parts, I didn't design them to be so strong and rigid. So for example, the holes that these little bearings go in were designed to be a little smaller than the bearing. So when I made this part out of PETG, I would just take the bearing and squish it into the hole, and the plastic, which is not as rigid, would just kind of deform around the bearing and would stretch, and then the bearing would be held very snugly by the very stretchy plastic. Now the new material is again more rigid, and so when I went to put the bearings in, they just went bonk, and then they didn't go anywhere. So I had to spend 2 hours sanding the inner diameter of all those holes a little bit at a time, because if I sanded them too much, then the bearings would be wiggly, and then you would get backlash and all sorts of other things. So I had to make them just big enough where the bearings would fit in. They still squish a little bit, so the bearings are held snugly, but that just was a whole process, which was very annoying. That problem where the material is too rigid also reared its ugly head when it came to these tiny little components that are part of the linkage assembly for each fin. So if we look at the linkage assembly here, we have a fin, and so we have This is what the fin looks like. this is the fin, CFPC, and this fin, this is what actually like sticks out of the side of the rocket like that. This red piece is basically permanently attached to the motor mount assembly, and then there's 2 screws where I screw the fin into that. And this red piece is connected to a little black piece that you can't actually see in there. Basically, it looks like this, and it's a horn that connects to the linkage assembly, which actually just connects to the servo horn. So there's kind of 3 components. There's the servo horn there, there's this main linkage here, and then there's this piece, which is actually black and way in there. So again, I printed all of these back out of the new material, carbon fiber polycarbonate, and these didn't work great. The biggest problem I had was with this piece here. So I print these kind of like this. I've tried printing them on their side before, which it's just hard to do these teeny little overhangs, but when I print these in this orientation, the hole diameter, like the effective hole diameter for these teeny tiny little holes there, increases. When you print things flat like this, and then it prints a teeny little circle, the plastic kind of oozes a bit, and so that circle typically closes. Actually, I just spent like 10 minutes spearing a piece of metal through this, so I actually had a hole in it. This hole was entirely blocked by plastic when it came off the printer. But when I print these like this, these holes are actually wider than intended, meaning that when I installed this piece in the linkage mechanism, the tiny little metal pins that I hope you can see here, they're like piano wire that connect each element of the linkage train. The little piano wires were wiggling inside of the holes, and so this fin had like 5 degrees of backlash. It would just go bump, 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 back and forth without moving the servo. Not very good. So I've had to go back and then grab all of these old pieces from the old version of this motor mount assembly that are made of squishy PETG, and I have to strategically choose which parts I need squishy and which parts I need strong, which again, I probably should have thought of beforehand, but here we are. I've decided that this piece, because it's printed like this, and this hole is like pretty constricted when it comes off the printer, is fine to use. It's very rigid, and it works great because there's not much like backlash or wobble of the pin inside of there. But this piece doesn't work. So I have to go disassemble all of these old linkage trains and then pull this specific piece out, and then that's what we're installing right here. Well, I finally got all the servos in, got all the fins in, got all the linkages in. It's looking really good. Cable managed a tiny little bit, mostly just wrapping it in Kapton tape and smacking tape to the side. Unfortunately, I think it's the texture or something, but the tape's not sticking very well. I just wanted to kind of keep the cables out of the way so they didn't drip kind of down into the linkage area here. So hopefully this stays. Kind of sketchy, but I don't really have a better way of doing it. I guess I could hot glue it or something. I don't know. All the fins, their backlash is tiny. I mean, I don't know if I can even show you in video here. That's the backlash without moving the servo. So, just a tiny amount. There's one that's worse. I think it's this one. A little worse. You can see here, this isn't actually moving the servo. You don't hear like the servo noise. But I think it's the servo horn is a little loose on the spline underneath it. I'm gonna have to fix that one later. This is fin 0, 1, 2, fin 2. A little funky, but yeah, they all look really good, really strong. So I need to put this guy together, get the raceway cable plugged in, assemble the whole thing, and then I need to measure mass properties. So I need to very accurately weigh the vehicle, figure out what its center of mass is with a motor and without a motor, and then I can use OpenRocket to help me get an estimate of its mass moment of inertia. So then I need to upload a file to its flight computer that has its mass moments of inertia, and its thrust as a function of time since liftoff. I need to modify one because I'm using a larger motor here and different mechanism. So I got to get that done, and then we'll do a little test, make sure that all the software works, and then we'll be ready to go. So I finally got everything put together, got the vehicle fully assembled, and then drove out to the launch site next morning. The last thing to do before launch is to align all of the fins and to make sure that their zero position is pointed directly upwards along the rocket. And once that was done, it was time to put it on the rail and launch it.
Launching in 5, 4, 3, 2, 1, launch.
In this next clip, you're looking down at the fins of the rocket via a mirror that is mounted to the side of the avionics bay. So you can see the fins there and then the red assembly that holds the mirror in place. And then in all these other areas, you can see the horizon upside down given how the camera's mounted. Now wait a minute, that didn't look quite right. Let's take a look at that parachute deployment again. So that is the end of our bulkhead, having sheared off of the avionics bay, attached to its parachute, now leaving the rest of the avionics bay to fall from our apogee altitude towards a swamp at the Johnson Space Center. Pretty unfortunate situation. Now the down-looking camera stopped recording right before we hit the ground, but the side-looking camera lasted much longer. So you could see by the time the motor burned out, we were traveling about 45 degrees downrange. This was unintended, and we weren't controlling pitch or yaw this flight, so that went uncorrected, which also meant that we were moving horizontally pretty fast. And when the parachute deployed, it just sheared the base of that bulkhead off. And then from the ground, all we saw was, as the parachute deployed, this little black dot falling away, and the rocket moving in its parachutes downwards towards the ground pretty slowly. So I knew that we had lost the AV bay in this kind of swampy area near the launch pad, and it's like an open field. So I figured we would just saunter over and go find this, but it was actually kind of buried in mud in this really swampy area that was no fun to walk around in. So it actually took a couple hours to find this thing in like an empty field, which is kind of surprising. But finally we did find it, and we're pretty excited because it was getting a little late. But once we found the avionics bay, didn't realize that this side-looking camera was actually still recording, and the vehicle was in much better shape than I was expecting, which was really nice. So here's how it looks now. Overall, it's not bad. There's a couple components that got damaged. Obviously, the bulkhead has seen better days. This was a pretty thin single piece of PETG that was epoxied into this tube coupler. I had to extend it a little bit because the antenna was too long. So this extended section here was just to give the antenna space. But the base here was actually a really thin piece of PETG. You can see that there's still infill in there, but overall pretty thin section. And then there was a single eye bolt through that transferred load into the base of this bulkhead, and then that transferred into the rest of this kind of red PETG structure, into the coupler, and then into the body tube. So overall, not a great design. Typically you'd have like a single large bolt through the center that transferred load all the way through the avionics bay, but I didn't have space for that. So I elected to just transfer it into the tube itself via one very thin 3D printed piece. Probably a bad idea. I think I can make this work though. I think with a different material, with thicker bulkheads, with more bracing here, I think I can still make this work. It worked for the first flight, which deployed its parachute in pretty sporty conditions. This one was just going horizontally, a little too much. But I have everything I need to make more of these AV bay tube sections. So I'll probably just end up remaking this and epoxying a stronger bulkhead piece here. And we'll try to fly it again. Nose cone, not looking good. It actually landed kind of nose down, but flat on the side of the nose cone, and there was grass that was shoved horizontally into a crack in the nose cone, which was pretty impressive. I didn't know grass was that strong, but nose cone, gonna have to make another one of those. But the rest of the avionics bay itself, other than being covered in grass and mud, doesn't look bad. The only part that's actually damaged is the battery mount here. There's a big crack running down its length. But when we found the AV bay, it was still powering the cameras, or at least one of them. So the side-looking camera was recording when we found it. The down-looking camera presumably was still getting power, given that the side-looking camera was working. But the SD card had popped out of its slot on impact, presumably. So it had stopped recording right before impact. But if I install the little plastic SD card covers that come with these cameras, I think I can make them more rigid. But yeah, the cameras look fine. So those look good. they're salvageable. The ACES board here was just, held in there for weight reasons. It wasn't actually powered or running, and it looks okay. The main flight computer was not running when we found the AV bay. So something was stopping it from getting power. Presumably, there was a short circuit somewhere, either on the separable connector interface here, which connects to our raceway cable. You can see it's covered in mud and grass and stuff. Or it was on any of these servo outputs, or there's a bunch of stuff on the back of the board back here, kind of low, that handles all of the power. So there's like a current sensing and reverse voltage protection, but there's a bunch of components through which all of the power flows to the main board. And if any of those shorted, then we probably would have lost power. Luckily, hopefully, that means that there's just one or two components that are damaged and then I can replace them. There's several fuses involved in the power management circuit, so hopefully it's just one of those that was blown and I can just replace that component, check for shorts anywhere else, and then salvage the flight computer. This is not the first time this flight computer has crashed. It has done it several times, but it always worked out okay. So I'm hoping that third time is the same and we can salvage it. The radio is actually a little bent here, just a couple degrees off. Should be kind of like this, but looks like the PCB itself has been bent and the antenna is kind of pointed that way a little bit, but it should still be okay. I also bent radios before and they work all right. So I will take this whole thing apart, get it all cleared off, get the mud off, and then start looking around in the main flight computer and see why it's not getting power. Well, you guys won't believe this. Still don't know why the flight computer was off when we found it, but it worked fine the whole time, and it just recorded its flight, it smacked into the ground, didn't care, and just logged everything to the SD card, which is absolutely nuts. This is the major event log, which is the text data log that it produces, and you can see we detected liftoff just fine. It's got some interesting control stuff in here. We aborted because of our roll rate was too high for a little bit. We'll look at that on video, and I actually have roll rate data from the cameras themselves. They actually have accelerometers and gyros on board, so I can compare this data with what the cameras have. And then detected apogee, 140 meters looks pretty low. Got to figure out why it thinks it's that low. It should probably be more like 250 or 300. Detected landing just fine, which only occurs if the total magnitude of acceleration is right about 1g, and our angular rate on each axis is pretty low and pretty stable. So this can only really occur after it hits the ground, and it just didn't care, I guess. And then it logged to the SD card just fine after that. After it lands, it waits a little bit more, and then it takes all the data from the flash chip, which is on the front right here, and puts it on the SD card in the back. You can see this kind of gloopiness and shininess. That's a conformal coat that I put on the board, which looks like it stopped any short circuits. What may have actually turned it off is if water connected these two pins together. When these are shorted together, then it deactivates the MOSFET through which all of the power goes. So basically, this is like a remove before flight pin. I can remove a pin and then it turns on the battery. And I think that's actually where it shorted, which is absolutely the best possible case, because then it just turned it off the way that I turned the flight computer off. It's like if the mud had flipped the switch to turn the power off. So that's pretty insane. I'm still going to check to make sure that nothing else is damaged on the board, but at least it logged the data. I have all of it, and that's pretty nuts to me that it just fell from several hundred feet and was totally cool with it. As far as the control system, it did enable this time, which was awesome, but I had set the gains way too high. So as soon as it enabled, it commanded maximum fin deflection one way and then maximum fin deflection the other way, and just started this really nasty oscillation that ended up with the system aborting because its roll rate was too high. So I need to turn those gains way down, do some more simulations, and figure out what the error was in my previous ones. But for the next flight, we'll have those tuned way down, and then we may try a little bit of pitch and yaw as well. Before the next flight, I also need to build a new avionics bay. So I have reprinted the aft bulkhead again. I've printed it. It's got much beefier ribbing on it. It's still out of PETG, unfortunately. I'd prefer to do it out of something like CF nylon, but unfortunately it needs to be transparent to RF because the antenna lives inside of it. So I don't think I can use a filament that's got carbon fibers in it, so I'm going to have to stick with PETG for now. But hopefully introducing some light pitch and yaw gains on the next flight will keep the vehicle pretty vertical. And I've also added a system where if we ever abort, the vehicle deploys its fins to their maximum deflection in opposite directions. So hopefully it just increases the drag coefficient pretty substantially, and we slow down. So when we deploy our parachutes, we don't have the same high horizontal velocity. So I'll get this thing put back together. Hopefully I'll fix some of the bugs with the GPS system, and I might even start ACES ground testing. But all of that is going to have to happen in a future video.